Hello everyone, I'm Yige Chen from Institute of Information Engineering, Chinese Academy of Sciences. This talk is about automatic protocol reverse engineering. In particular, I'm going to introduce the problem in realizing automatic reverse engineering and how we employ semantic fields to solve the problem. First of all, I would like to introduce two kinds of protocol reverse methods, namely protocol reverse methods based on execution traces and protocol reverse methods based on network traces. The protocol reverse methods based on execution traces conduct protocol reverse engineering by directly debugging the protocol binary or monitoring how the protocol binary generates and passes messages. However, we must obtain the corresponding protocol binary programs in advance. Because these methods can dissect the real binary program, the accuracy of the inference results is generally high. Some private protocol developers may use obfuscation techniques to sort protocol specification inferences, such as binary packing, eliminating unnecessary instructions, and replacing call with indirect jumps. The methods based on network traces only takes the network traces of the target protocol as input, and the obtaining of network traces is more straightforward. When the binary programs are available, we can collect the network traces by passively monitoring the network gateway through port mirroring switches. The basic inference framework of these methods is first clustering messages based on their group characteristics and then performing specification inferences within each cluster. Next, I would like to introduce four related protocol reverse methods based on network traces. The first work, discover first tokenize messages into a sequence of text and binary tokens, and recursively identify the format, distinguisher, and clustering. Prodecoder first uses n-gram sequences to represent messages and exploits latent directed allocation to select the keywords in the messages. Then, prodecoder uses information bottleneck as clustering metric to partition messages into clusters based on their keywords. NetZope also introduces contextual and thematic information as a key parameter to cluster messages and partition the fields in the message. ProWord formulates the protocol reverse engineering as an information retrieval problem and focuses on extracting protocol feature words from network traces. They first modify voting expert algorithm to extract feature word candidates, and then selects the desired feature words based on the frequency, location, and the length of words candidates. In our work, we propose a semantic-driven approach named Inspector to conduct automatic protocol specification inference from network traces. The system architecture of the inspector is shown in the figure. The system contains three phases, including length field inference, message type inference, and format inference. When we collect network traces, we first need to recover the original dialect message in the same way as the communication parties. For the packets transmitted by TCP protocol, we reassemble them into original message to ensure the integrity and takes it as system input. The datagram transmitted by UDP protocol is naturally integrated, so we directly extract the payloads and regard them as individual messages. The primary purpose of the length fields in the message is to specify the boundary of the variable length payload, so the communication parties can accurately extract the relevant payload from sequential binary messages without explicit delimiters. Thus, we select the correct length field pattern based on a reasonable assumption that the correct length field pattern should be more frequently appeared than the wrong ones in the messages and can be well explained. There are two main difficulties in seeking the length fields. The first difficulty is to deal with the hierarchy of the length fields. From a vertical perspective, only the length fields in the top level can be directly related to the size of the message, while other length fields are only related to the size of relevant payload. From a horizontal perspective, there could be multiple parallel length fields in the message, which weakens the correlation between the value of length fields and the size of the message. The other difficulty is to deal with the various interpretation of the length field. The length fields in different protocols may have their preferred specifications, such as in terms of position, indianness, and bit width. To be specific, the length field could be located before or within the relevant payload. The indianness could be little endian or big endian, and the bit width could be 8, 16, 32, or 64 bits. In order to solve these two problems, we propose a hierarchical length field model to perform the length field search in a certain routine and develop a corresponding algorithm to implement the length field inference. The figure shows the structure of hierarchical length field model. In this model, the basic structure units of the message are tuples that are arranged in sequence or nested recursively. An ordinary tuple contains prefix fields, a length field, and a payload. The prefix fields typically provide meta-information of a message, such as message type, protocol version, and session ID. The value of the length field determines the size of the subsequent payload. The contents of the payload could be sequential bytes, or a subtuple that should be passed in the lower layer. The suffix fields are optional with respect to the protocol format, which may store the message authorization code of preceding byte sequences. Based on the hierarchical length field model, we develop an algorithm for the search and selection of length field pattern candidates. Similar to the length field, the message type field is also a semantic field that plays a key role in the proto-format inference. The message type field usually indicates the specific format type of the message when it exists, so that the communication parties can reach a consensus on the structure of relevant payload. Therefore, when we find the message type field in the message, we can further cluster the messages with the same format type. Then, we can exploit the hierarchy of the length field pattern to perform preliminary clustering and make the messages in each cluster share the same length field pattern. The main iteration in identifying the message type field is that the number of unique message types should be limited to an operator range, and the sizes of the same message type message are relatively close. The figure shows an example of the message type fields in the TLS messages. According to RFC document, the byte field at offset 05 is a top-level message type field, which is marked with a light blue background in the figure. In this example, the message type field uses continuous value from 14 to 22, while other fields take fixed or random values. This phenomenon only appears in the cluster where observed messages belong to the same superior format, and the message type field is used to distinguish different infra formats. After obtaining the length fields and the message type fields, we can exploit these fields to cluster messages with the same format, and then perform protocol format inference for other fields. After obtaining the length fields and the message type fields, we can exploit these fields to cluster messages with the same format, and then perform protocol format inference for other fields. Similar to Discoverer, we specify the inferred format as a sequence of token specifications, and use the token properties to describe field specifications. When the token takes the same value across in all messages, we consider it as a binary constant token. When multiple consecutive tokens take a variable value within ASCII coding range in all messages, we consider them as text variable tokens. All tokens outside the above cases will be considered as binary variable tokens. We evaluate the inspector on three widely used binary protocols, namely TLS, SSH, and MQTT. The TLS is a binary application protocol that primarily aims to provide privacy and data integrity between network communication parties. The SSH is a binary application protocol that provides a secure communication channel for the client and server. The MQTT is a lightweight, unencrypted message protocol that is designed for the IoT communications. The ground truth specification details of these three protocols are available in the online RFC documents and OSIS standards. The presentation of experimental results includes the message clustering and format inference. Except for one format of the protocol SSH, all message clustering results correspond exactly to the ground truths. The table shows the summary of message clustering results. For the protocol TLS, 12 messages clusters correspond to all 12 true formats in 100% accuracy and cover 100% messages of the datasets. For the protocol SSH, the inspector finds 9 message clusters that correspond to 9 true formats in 19% accuracy and cover 99.6% messages of the dataset. For the protocol MQTT, the inspector finds 21 message clusters that correspond to 21 true formats in 100% accuracy and cover 92.7% messages of the dataset. This experimental result shows that the inspector can perform very well on the message clustering and can automatically filter out unformatted messages from the clustering. The two tables shows the detailed protocol inference results for TLS. As shown in the table, we have inferred 12 protocol specifications. We can find that the 5th to 12th formats contains 2 levels. The orientation are all after. and the indianness is big. Those two tables show the detailed protocol inference results for SSH. As shown in the table, we have inferred 9 protocol specifications. We can find that all formats contain one level. The orientation are all after, and the indianness is big. The detailed protocol inference results for MQTT are similar, which contains 21 protocol specifications. This is all of the presentation. For more details, you can contact me by email. And thanks for your attention and hearing.